see your presentation is ready, so the screen is yours. Oh, we cannot hear you.
Hello, can you hear me now?
Now we can, yes.
Okay. Thank you so much for chairman. And it's my honor to present our work in this conference. Hello, everyone. Good afternoon. My name is Hongjian Zhou, come from Hefei Institute of Physical Science, Chinese Academy of Science. Today, my presentation work is selective capacitive deionization in pseudocapacitive electrode. Sorry, a little bit changed my presentation title. So this is my presentation outline. So firstly, the Chinese, sorry. Firstly, the Chinese academic engineering mentioned that the treatment on the recycling technology of high salt wastewater is a global engineering frontiers such as water purification, seawater desalination, nuclear wastewater treatment, and lithium extraction, and so on. So our CDI have the advantage such as high selectivity, low energy consumption, and no secondary pollution. So it has an important application prospect in this field. We compared the three major water purification technology with CDI. We can find out that the CDI have the high selectivity than other technology, and also no need the chemical reagent additional, and even have the high chloride iron tolerations. So it have the good application, good advantage. This. So nowadays there are so many application protect by using CDI technology in the water treatment, such as the hard water softening, water desalination, and the water purification for removal some pollution, and even the precious metal resource exploitation is the hard research area in CDI field. But the all key issue we think we should develop the high efficiency CDI electrode materials. So we're curious how to using the CDI technology to treat and recycle the high salt wastewater. We can do the three parts. One is the electrode material. We should improve the absorption capacity and selectivity of target iron. Second part, we should explore the mechanism, study the interaction rule and the interfacial chemical reaction and the transformation mechanism between the target iron and electrode. But the most important part is the modular structure. We can do the optimizing the electrode stacking and the flow path structure to improve the effective area utilization and the charge transferability of our CDI device. So now next start is we developed some high performance CDI electrode material. So first one is the pseudo-capacitive desalination built by the valence engineering with the manganese oxide. Some researchers have been demonstrated that the manganese oxide with the different crystal structure can show the different desalination performance. But as we know, the manganese oxide also have the different valence state, such as the divalence, trivalence, and the divalence, trivalence mixed together the manganese oxide. So we try to using the manganese carbonate as the one same precursor to develop these three types of manganese oxide. One is the manganese oxide, manganic oxide, and the manganese oxide. We try to find out these three different oxide material can have the different desalination performance. So this is our synthesis of the material. We using the different characterization technology to character our material. By using the TEM, SEM image, we can see all three types of manganese oxide. The morphology is almost similar in spherical shape. And also this electrode property, this is the electrode property of manganese oxide. We can find out all manganese oxide have the characteristics of sodium storage by pseudocapacitance, and also the higher manganese valence state, the higher capacitance contribution ratio we can find out. And this is the MCDI desalination performance of manganese oxide. We can find out the divalence, trivalence, the divalence, trivalence mixed together, the manganese oxide all have the high salt absorption capacity, and also they have the good average salt absorption rate in the 500 ppm nitrogen chloride solution, benefiting from their intrinsic electrochemical.
Looking forward to your presentation, and we're ready to go.
The most important part is the
rest
manganese oxide. This material shows the best electroabsorption performance. So we combine with the DFT calculation and the experimental result, we can find out the lower manganese valence is more suitable for this CDI desalination. Whatever for the electroabsorption capacity and the cyclic stability than the high manganese valence oxide material. This is our part. Second part is we try to using the CDI technology for the selective removal hardness iron. As we know, the hardness iron in the water could form the scale in the equipment. Currently, the common treatment method is the ion exchange race, but the race regeneration requires a large amount of nitrogen chloride, resulting in the excessive salinity of groundwater. Now, in America and Europe, try to prohibit this technology for the hardness water treatment. But our CDI have this advantage. So we try to find out what material can do this. In the end, we find out the manganese ferrite, this material can have the good selective removal of the hardness iron. By we using the one-step thermal method to develop our material. We're using this material as a cathode for the hybrid CDI desalination. This is our material morphology and the crystal characterization. This is the electro performance. We can find out our material shows excellent absorption property for the calcium and the magnesium iron. And the material shows the prominent capacitance of 534 micromole per gram calcium iron, and also the 980 micromole per gram magnesium iron, which is outperformed than other material as reported. And in the end, we also curious what's the mechanism behind the material for the selective removal hardness iron. By using the electrochemical characterization, we find that the uniform and pseudocapacitive affinity based on the synergistic effect of relative redox potential, and also the ionic radius and valence, but in which the redox potential is the dominant factor. And also this material, we try to running for 5 days the hardness treatment. Our material shows the good stability. And the third part, we try to develop the carbon combined with the pseudocapacitive electrode. As we know, the pseudocapacitive electrode, most people worried about the stability. So we try to using the carbon nanotube to encapsulate this our material to enhance the stability. We utilize the melamine form to prepare nitrogen doped carbon nanotube encapsulated iron heptatalcasulfide nanoparticle for the pseudocapacitive removal of the lead iron from water. And in this TEM and SEM image, we can see that the carbon nanotube covered our material inside. All the Fe7S material encapsulated inside of CNT material. So this is the electrochemical property of our material. We can find out the CV curve presents the distorted rectangle-like shape, exhibiting the typical pseudocapacitive behavior. And also the GCD curve maintained their original shape after 330 cycles, suggesting that our material have the outstanding long-term durability for reversible charge discharge. So it can be using in the CDI absorption. So this is the CDI performance. We can find our material shows the excellent lead iron remove capacity. The maximum value can approach the 237 0.8 microgram per gram at 1.2 voltage applied voltage. And also the material shows the superior cycling stability during the 16 absorption-desorption cycles. And it maintained about 91% for the original capacity. And we try to using the XPS characterization to figure out the behind the mechanism. We figure out that in this XPS the result, we can find out the strong bonding force between the lead iron and the sulfur under the electro field is confirmed, and also under the high background of high source, the removal rate of lead iron can still reach about 90%. So it can have the selectivity. We try to using the DFT simulation to prove the selectivity mechanism. We can find out our material have the best absorption affinity for the lead iron among the other occasions. For example, the nitrogen, calcium, so on. And also we can see that the main absorption site for the lead iron on the 206 crystal plane is the cavity formed by sulfur ether. So next part is the last part. We also do the seawater desalination by using the FCDI device. As we know, the FCDI have the good advantage compared with the CDI. One is the high absorption capacity, also stable operation and continuous operation. But they still suffer some defects, such as the low absorption rate and poor charge utilization. So we try to improve the FCDI desalination by changing the current collector structure. As we know, the traditional FCDI device using the snake-shaped flow channel, but we try to develop the novel Archimedes spiral flow channel. Why we do that? Because we do the CFD simulation, we can find out in the snake channel, the flow rate is not uniform. In the straight line, the flow speed is fast, but in the corner side, the flow rate is slow. So the whole flow voltage is not uniform. So, but in our spiral flow channel, the all flow rate is uniform. And this is our mechanism, our experiment result. We can find out this structure improved twice time. So okay, I will speed up. And after finish that part, we call the 2D binary electrode channel. We think it's not enough, so we developed the 3-dimensional form current character. This character shows the more enhancement for the FCDI desalination performance. We can find this. We get the 3.27 time improvement. And also the charge transfer area is larger than the 2D binary. And also we try to explore the cycling stability for the FCDI. We try to do the 100 cycle operation, but all still is stable. And we also using the real seawater to evaluate our FCDI device. We can find we try to do the simulated seawater and the South China seawater desalination for the long-term operation. In the end, we get the 99% desalination ratio. And I would like to finish my presentation. Okay, thank you. Thank you so much for your attention.
Thank you, Professor Zhou, for this good introduction to almost all of your work, I think.
Thank you so much. Yeah,
it was really impressive. So now there's time for one or max two questions. No? Okay, I have one for you. I think we can take before the next one. Just a clarification question, because in one of the first slides you mentioned that lower valency was more suitable for CDI of the manganese oxides. But what I could see from your data and what you also wrote was that the higher valency provided higher capacity.
yes.
So can you elaborate how that goes together?
Yes, this one, right?
Yeah.
Yes. We also curious in the electrochemical property. We find out the higher manganese valence state shows a good capacitive contribution ratio. But in the end, in the CDI part, we show the lower valence state. They show the good desalination performance. We still try to figure out this question, but we couldn't get the answer. Sorry.
Yeah. Okay, no, it's a work in progress, I guess.
Yeah.
Thanks a lot, Professor Zhou. So let's give him a hand.
Okay, thank you so much. Thank you.